All right, let's jump right into this explainer on what has to be the universe's most mind-boggling magic trick. We are talking about an invisible, silent force that we all interact with literally every single second of our lives. I mean, it's the very thing holding you in your seat right now. Today, we are decoding gravity. And don't worry, we're going to break this down conceptually, completely step by step, with absolutely no complicated math, so that anyone can easily understand the invisible rules holding our universe together.
So have you ever actually stopped to think about the fact that you are standing on a giant, rapidly spinning ball right now? Seriously, think about it. If you put a little toy on a spinning top, it just flings right off, right? Yet here we are, perfectly anchored to the ground. We aren't floating away into the sky. Why exactly are we stuck to this giant, spinning rock?
Or consider something really mundane, like dropping an object. If you let go of an apple, it drops. But why doesn't it ever zip to the left? Or, just hover there in midair? Why doesn't it ever fly straight up? It always, without fail, drops in one highly predictable direction, straight down. What exactly is down there pulling on it?
And if we look up at the night sky, we see the moon. Now, we all know from everyday experience that to spin a stone in a circle, you have to tie a string to it and hold on tight to give it an inward pull. So how does the moon just endlessly circle our planet without some giant invisible string keeping it from flying off into deep space? Where is that inward pull coming from?
Well, the single, spectacular answer to all of these questions is the gravitational force. It basically acts like an invisible cosmic glue. It's the exact same force that anchors you to the spinning Earth, pulls that apple straight down, and provides that inward pull, acting just like our invisible string, keeping the moon safely locked in its circular dance around our world.
Let's move into section 1, Newton and the apple.
So Isaac Newton made this absolutely massive leap in logic. He realized this pull wasn't just some special magic trick belonging only to the Earth. It's actually a universal rule. He proposed that every single body in the universe attracts every other body. Meaning an apple attracts the Earth attracts the moon, and yes, right now, you are literally gravitationally pulling on whatever screen you're watching this on.
Which brings us to section 2. Size and distance matter.
To understand how this works, first, you need to know that size matters. Gravity is always a team effort between two objects. You can kind of think of it like a handshake. If two tiny apples try to pull on each other, it's a very weak handshake. But if you pair a tiny apple with the gigantic, massive Earth, their combined teamwork creates an incredibly strong handshake, giving us a massive pull.
It's a totally direct relationship. If one object gets heavier, the invisible rubber band between them gets thicker and pulls harder. And if both objects get huge, well, that invisible pull becomes intensely strong.
Okay, so we know big things pull hard. But what happens when things move further apart? If you take those two objects and push them away from each other, increasing the distance between them, how does that invisible pull react?
Imagine you're shining a flashlight at a wall. Close up, the beam is bright and really concentrated. But as you step back, that exact same amount of light has to spread out over a much wider area, so it gets dim very quickly. Gravity works the exact same way. If you start with a strong pull of, say, 36 at a distance of 1, and you take just one step back to double the distance, the force doesn't just safely cut in half. It plummets, crashing down to 9. It becomes 4 times weaker. Take 3 steps back, and it's 9 times weaker, dropping all the way down to 4.
Scientists call this rapid drop-off the inverse square law, but honestly, all you really need to remember is this. Gravity is incredibly clingy up close, but it gives up remarkably fast the moment you start moving things apart.
All right, let's look at section 3, why don't we stick?
So if every object attracts every other object, you might be looking around right now wondering, why aren't I suddenly sticking to my furniture? Well, the secret is that the base level of gravity is actually unimaginably weak. To calculate the pull, scientists use a base number that starts with 0, a decimal point, and then 10 more zeros before you get to a 1. It is infinitesimally tiny. So between you and your coffee cup, the gravitational pull is technically there, but it is just the weakest, most pathetic magnet you can possibly imagine.
You don't stick to your furniture because you both have relatively small masses, creating a pull that is practically 0. You'd never feel it. But you definitely stick to the Earth because the Earth has a truly colossal mass. It's so unfathomably huge that it completely makes up for that tiny baseline number, creating a pull strong enough to anchor you safely to the ground.
Moving on to section 4, the rules of gravity. Let's clear up a few basics. Rule 1, gravity is exclusively an attractive force. Unlike magnets, which can push away from each other, gravity only pulls. There is absolutely no such thing as a gravitational push. Rule 2, it completely ignores obstacles. You can't build a gravity shield. It passes perfectly through air, water, thick solid rock, or the empty vacuum of space. And Rule 3, it always pulls straight along a direct line connecting the very centers of the two objects.
In fact, because of that last rule, scientists treat planets as what they call point masses. Why? Well, imagine looking down at a massive mountain from an airplane cruising at 30,000 feet. From way up there, the huge mountain just looks like a tiny speck. Distances in space are so ridiculously huge that mathematically even gigantic planets are treated like tiny single dots, pulling entirely from their dead center.
And finally, Section 5, Action and Reaction.
Now here is where our common sense gets completely flipped upside down. Because gravity is a shared bond between your mass and the Earth's mass, that teamwork goes both ways. The Earth pulls you downward, sure, but you also pull the Earth upward. And because it's the exact same shared connection, the force the Earth uses to pull you down is exactly identical to the force you are using to pull the Earth up. It is perfectly equal.
Think about the sheer scale of that for a second. Your body is pulling up on an entire planet with the exact same amount of force that the planet uses to pull you down. So the next time you feel grounded, firmly planted on the floor, I want you to ask yourself this: are you stuck to the Earth, or is the Earth stuck to you?